This set of animations is about two different types of functions that are useful in statistics, and in situations that you will need to describe mathematically. The first type of function takes values on the horizontal axis and assigns them to values on the vertical axis. These kinds of functions involve covariational reasoning, because one varying quantity is mapped to another varying quantity. The second type of function assigns a next value to a given value. But, for this kind of function, it may not be easy, and it might even be impossible, to know the value of the nth term in the series. Next, you will see some examples that illustrate this point. Here, the arrows are pointing to odd numbers, and here, the arrows are pointing to the even numbers. You should be able to write a formula or rule that gives the nth even or odd number. Similarly, the nth term in other sequences also are not difficult to describe using covariational reasoning. Several examples are given on the following screens. Next, some examples are given in which several different rules may exist for describing a series of numbers. For this example, you might notice that the first term skips one number, the second number skips 3 numbers, the third number skips 5 numbers, and so on. Or, you might notice that the first number is 2 times 1, the second number is 3 times 2, the third number is 4 times 3, and so on. Or, you might notice that the first number is 2, the second number is 2 plus 4, the third number is 4 plus 6, and so on. Or, perhaps you see some other way to describe the nth term in a series. This example is the famous Fibonacci sequence. What rules can you find to describe this sequence? These graphs and tables show one reason why the functions that we have been looking at are important in statistics, and in other situations where we need to describe things mathematically. As you already have seen, one thing that we will need to be able to do in this course is to define functions that fit a collection of data. And, in statistics, linear functions and polynomial functions are especially useful. In past examples in this course, you have seen how polynomial functions can result from multiplying linear functions or from adding monomial functions. And, the table and graph in this worksheet show how polynomial functions also can result from accumulating functions. For example, in this graph and table, notice that f1 is a constant function. f2 is accumulating the values in f1, and f2 is accumulating the values in f2. Furthermore, they also show that f1 is the constant function, f2 is the linear function, and f3 is the polynomial function. Similarly, if you scroll down this worksheet, you see that If you start with any polynomial function and if you use a table like the one shown here to calculate differences between values at regular intervals, then the second column of differences always reduces to a constant function. What this implies is that, for many real-life situations that involve constant functions or linear functions, polynomial functions often arise as accumulations of the constant or linear factors.